All right, it's recording. Here we go. Exercise 3I. This is from the Year 11 Methods textbook. Chapter 3I. This is when it finally ventures into, to me, something new and not your typical 9 to 10 stuff. So let's recap just this bit again. This is called b squared minus 4ac. This is called what again? Discriminant. And the symbol for it is a triangle. Okay? The discriminant is found in where? Which formula? Quadratic formula. Now, let's see how many of you remember the quadratic formula. X is equal to, yes, Andrea?
Negative b plus minus b squared.
Wrong. All right, stop there. Follow on with next. Violet? Beautiful. Just missing the square root. So, this is your quadratic formula, and we know that we can find that by simply doing let y equal to 0 to find the x-intercept, and then you do completing the square, and then difference of perfect squares to get there. Yeah? Well, you don't have to do difference of perfect squares to get there, but this is the formula. But the key part was what you're square rooting. That is what we're focusing on, b squared minus 4ac. We then, and I tried to explain it to you, I said to you that let's think about it logically. If what you're square rooting is less than 0, what's the problem?
There's no solution.
No solutions. Why are there no solutions? Can I please have Una? But how do you know? It is true. It means no x-intercepts. Why is it that when the discriminant is less than 0, there are no x-intercepts? Very good. So that means this is broken. So that formula is to find x-intercepts, right? And if you can't square root a negative number, so say root of negative 9, no matter what b and 2a is, it doesn't matter what these two numbers are, you plus or minus and you can't square root this number, then it's broken. So you type that in a calculator, it will just come up as error because they can't resolve that issue. Okay, so that's why if it can't be resolved, it doesn't mean you've done anything wrong. It just means the quadratic likely has no x-intercepts. Okay, that's why we say no solutions or no x-intercepts is what it's trying to say. Notice that why the language? Why do we say no solutions rather than no x-intercepts?
Because when you solve the quadratic formula, there would be no solution. You can't solve for it.
It is true. Actually, I should probably guide you on that. There's a reason why they say no solutions, no x-intercepts instead of no x-intercepts. When I'm explaining it to you specifically for this situation, that we're actually trying to find the x-intercept, then yes, there are no x-intercepts. But what's beautiful about this concept is it doesn't have to be always to find x-intercepts. You can end up with any quadratic based on whatever problem you're trying to solve. Then the question is, how do you find a solution to that problem? And that's where 3J comes in. So 3J is not finding x-intercepts. 3J will be finding something else. And you happen to fall into this situation. That's why when there is no solution to it or no answer to it, it's not that there's no x-intercepts. It's just that you can't solve it. That's the technicality to it. Yeah.
It's kind of based on what you said, but when I was doing the textbook questions, it kept asking like no real solution.
Yes, so that's even more specific. So it's not just that no solutions means there's no answer that we can come up with. But when you say no real solutions, it's very specific. Real is the mathematical term for saying any number. Has anyone seen this symbol before? Capital R? Which is also meant to equal negative infinity to infinity. Okay? Capital R in mathematics means real numbers. So that's what they mean, but we haven't taught you that yet. It's called, in the set of numbers, when we're talking about different set of numbers, you can work with positive numbers, whole numbers, fractional numbers, integers. Then R is one of the letters. And in a nutshell, when you say R, it just means any number that you can think of at the moment. So any number that you can come up with, that's in the real world. When you do specialists, or if you do 10 enhanced next year, you may start to learn complex numbers, which then introduce the idea of imaginary. So then you have real numbers and then you have imaginary numbers. Okay, but that's for something else. I'm just going to deviate from that before you get confused by that. Okay, so I'm going to delete that. Yep. You are already learning functions. You just haven't learnt the proper definitions for it. Yeah. So this technically is a function. That's a function. But you just don't know what a function is yet, like definition-wise. But that is a function. Yeah. Now with the deviating, there'll be too technical. All right. Let's carry on. So we're back to this. No solutions means that when the discriminant, or what you're square rooting, is negative, so then clearly you can't solve it, so hence no x-intercepts. And then what's the logic if the discriminant, so whatever you're square rooting, if it was negative b plus minus square root and it's equal to 0. So if the discriminant is 0, what's special about that? Yes, you know. It is the turning point, but I'm looking for something, like that's the overall picture, but I'm interested in what happens. Why is the root of 0 so special compared to, say, no less than 0 before? Anyone? Yes, Raha?
Whether you do plus or minus, you get the same answer, so there's only one solution.
That's key. Okay, so this is one of the things. So negative b plus minus. Now, root of 0 is just 0. But you realize that whether you add or subtract 0, the answer is still going to be the same. So no matter what b and a is, you're always going to get negative b over 2a, which means there's only one answer. That's why they say this is there's one solution to this problem. Well, technically, in our scenario, it's one x-intercept. But the only way for a quadratic graph to have one x-intercept is when the quadratic has the minimum either the minimum touching the x-axis, so the very lowest point touches the x, it just hits it and it goes back up, or you have a maximum turning point where it touches, again, at the maximum value, it touches the x-axis and it comes back down again. Those are the only two scenarios where you can have one intersection. And that's the only reason why you get one solution. Then your final part, which is very logical, if the discriminant is positive, well then negative b plus minus square root of whatever the number is, doesn't matter what b and a is, we know the result's going to give you two distinct differences. One's going to be plus that number and one's going to be minus that number, so of course it's going to be different. Because you're really just getting negative b over 2a and you're adding wherever the root of that number is, or you're getting negative b over 2a minus the root of whatever the number is. These two cannot be the same. They have to be very different. So that's the scenario that describes where you get a quadratic with two solutions. And that's why they say two solutions for that scenario. Okay, so that's the theoretical understanding. Rather than doing what most mainstreamers do, is they just memorize this. So they'll memorize less than 0, no solution, equals 0, one solution, greater than 0, two solutions. Problem with that is that at some point in the test, I can tell straight away if they get what a discriminant is when they get it all wrong. So they just mix it all left and right because they don't know what they're doing. Okay, because there's a point to understanding this, and it's really just understanding what happens when you square root the number. Why is that so key? Okay, Sonny, you might need to get a chair. I think we're out of chairs here. So as you put your stuff down, maybe pop into another class, get a chair. All right, here we go. Let's do example 1. So we're going to practice what is this year 11 content. So this is year 10. This is just, when I normally teach my year 11s, I recap what they've learned in year 10. And then I try to explain it so they have an understanding of the formula, what's happening. Then I introduce them to the first kind of thinking. So this is the kind of thinking that challenges their understanding. Here's an equation. Let's just take the first bit here. Let's say I gave you this equation. I say y is equal to, and then we've got a quadratic equation. It's 3x squared minus 2 times m times x plus 3. Now the problem here is we can't sketch this equation yet because we do not know what m is. If I took off m, then you can then use the skills that I've taught you so far and you can sketch the graph. Find the y-intercept, factorize to find the x-intercept, and then complete the square to find the turning point or use my formula, right? But the problem is the m. The m now, we don't know what m is. M can be any number. So that means my equations can be many different types of equations. It could be this. Here's an example. So if m was equal to 1, then the equation that I would get is 3x squared minus 2 times 1 times x, which becomes 2x, plus 3. You get one type of graph. But if m was equal to 2, then you'll be sketching y equals to 3x squared minus 4x plus 3. So that's a second graph. If I then switch it up and I said m equals to negative 5, then now you get y, the third equation is you could get 3x squared, plus 10x plus 3, right? Now in each one, what the question's asking is, for what value, so what should m be? So what should m be? 1, 2, negative 5, negative 100. What numbers can m be so that I can guarantee I have one solution? Meaning, there's only going to be one x-intercept. So looking at this straight off, none of us will be able to tell straight away whether this has one x-intercept or two or none, or 1. We don't know. And what you don't want to be doing is you don't want to sit there and go, let's find the discriminant for this, let's find the discriminant for this, let's find the discriminant for this. It takes too long. There has to be a better way to figure out what numbers can I choose for m. And this is what I do when I make up your test papers. I may have certain numbers I actually already want. Whether I want one solution, 2 x-intercepts, no x-intercepts, so what kind of problem do I want to give you? I then figure out what I want first, and then I figure out the m value to make it harder or easier, fractional or not fractional, right? So you get the power to play around with this m. Now I'm going to show you just visually what's happening, and then we'll talk about the skills that you can apply to solve this problem, okay? Let's go to Desmos, our fun Desmos. I know, back to Desmos again. All right, so here we go. We've got y equals 3x squared. We've got, was it plus or minus? Minus. So we got minus 2 times m times x plus 3. It says add a slider for m because we don't know what m is and we're going to vary it. So if m was 1, which we tested just now, 3x squared minus 2x plus 3, unless you have the ability to look at an equation like this one and be able to picture the graph immediately like Desmos, then you can already tell me there's no solutions when m equals 1. Oh, you didn't get one. Sorry. All right, let's try. What do you think will happen if I have m equals 2? So let's see. We said m equals 2. You should have 3x squared minus 4x plus 3. Let's see if that has 1, 2, or no solutions. Here we go. Still no solutions. So let's try negative 5 and let's see what that looks like. That has 2 solutions. So somewhere between negative 5 and 1 and 2, somewhere between negative 5 when m is negative 5 and 1 and 2, somewhere there must be one solution and then no solution, right? Because the quadratic went 2, at some point it had to be 1 for it to be none, right? So the question is, where's that boundary? How do we find out? Now you can sit here and keep trial and erroring, but if you do that, this is essentially what you'll be doing. You'll be subbing in negative 4, now it's still 2, negative 3, still, oh, that's looking like 1 there, so you're like, oh, cool. M equals negative 3 gives you 1, and then you might try negative 2, it's like, oh, that's none, negative 1. So it looks like, what's the pattern so far? Very good. So if I told you m was 10, how many solutions did you predict now? Oh, I'm surprised on how you figured that one out. But yes, so when m equals 10, we got 2. When we had m equals 2, it was none. 3, it's back to 1 again. 4 is now 2. So there's a pattern here, right? But if we had to do this by hand, you would have had to test how many numbers just now? You would have tested 10 numbers, found 10 different discriminants. That would have been crazy to do. It's so inefficient, right? So this exercise is going to teach you to do it better And in order to do it better, you have to learn all the skills that you did well on the very first test. It means you have to be able to sketch, you have to be able to analyze the problem. Okay, so that's what I teach you today. So hopefully you didn't copy this bit, but if you did, that just gives you a precursor of the bad, inefficient way to do it. Let's look at the more efficient way. So, how do we do it then? So, notice the thing that we're really focused on was we're actually going to test it by figuring out the discriminant. So then we say, all right, well, why don't we do a hypothetical discriminant then? Here we go. Here's our equation again. Y equals to 3x squared minus 2mx plus 3. If I were to use the discriminant, I need to know B, I need to know A and C. What is my B? What is my A? And what is my C? Let's go with Sean. What's my B? We'll be careful. Negative 2m. So this is where in the mainstream I do normally got to catch out on that. That's why I put B first, because it's the coefficient of x. It's what you're multiplying to x. So in this case, this is your B, not just the number. That's what you've been doing so far, but just understand it is the number that's multiplying to x. So that negative 2m is your B. So that's my new B. What is my A in this case? Can I please have Sanvi? 3, very good. It's the coefficient in front of x squared. And then finally C, which is the constant term, meaning there is no variables to it. Which one is that? Let's go with Olivia. 3, very good. The signs matter as well. Okay, so 3, that's positive, and then that's negative 2m. Now, that means if I were to then find the discriminant, it's not going to give me a value, okay, because we don't know what m is, but that's okay. We're going to study that, okay? So this whole exercise is to study this function. So here we go. We've got B, which is negative 2m squared minus 4 times A, which you told me was 3, and times C, which was 3. This gives me the discriminant function or rule or formula as 4m squared, because square of negative 2 is positive 4, and square of m is m squared, or negative 2m times negative 2m becomes positive 4m squared, and minus 4 times 3, which is 12, and 12 times 3 is 36. This is a formula to tell me what my discriminants are when you have m. Now that means if I sub 1 in, I can tell whether I'm going to have 0. If I sub in 2, I can tell how many solutions I'm going to get, because if it's positive, you get 2. If it's 0, you get 1. And if it's negative, you get none, right? So remember that? So remember we said, if the discriminant, whatever m you choose, if discriminant is positive, you get 2 x-intercepts. If discriminant is equal to 0, you're going to get 1 x-intercept. And if discriminant is negative, well, you can't square root it. So hence you get 0 x-intercepts. Now, instead of trial and error, which is what we were doing before, instead of subbing 1, subbing 2, subbing negative 5 for m, to see the answers, the most efficient way is to sketch that. And this is where the Year 11 method students have a lot of trouble to visualize what I mean by that. You see, you don't always have to have y and x. That can still be your y-axis values. And this is your x-axis values. Okay, if you can do y and x, then you can do discriminant and m. So what I'm trying to say is you are going to graph and have a look at the pattern of the discriminant. But you have to remember, this is now not the y values. This is now the discriminant values, meaning this is when it's positive, this is when it's 0, and this is when it's negative. Just like what we were saying. We were saying if it's positive, so any positive discriminant values, anything in this region will mean that you have 2 solutions, or 2 x-intercepts. Anything that hits exactly when discriminant is equal to 0, then that means that's when it's 1. And then any part of the function, the graph that you see that is below the x-axis, this is when discriminant is negative, so you get no solutions. Okay, so this is our m. So just kind of treat it like, I'm going to write a different letter over here just to help you visualize. So m and x, y and x. What I'm asking you to do is sketch this graph. So if you've done much harder ones on the test, what I'm asking you to do is sketch this graph, but you have to switch your head. It's not y anymore. It's actually discriminant. And instead of x values, this is the possible m values you're going to choose. Okay? So, what does 4 minus m squared minus 36 look like on this graph? Or if I change the language just to help you keep up with me here, if I said, what is the graph of 4x squared minus 36 look like? Can anyone read it? Okay, so it's a positive, it's a smiley shape, so we can tell. It's positive 4, so it's a smiley shape. What else can we say? What's the y-intercept?
Arguments. How can you get smiley face? Because x can be anything.
No, we're not talking about x, we're talking about m for now. Yeah, so we're looking at, I called it x just to help you visualize it, but what I'm saying is you're actually sketching this graph. So as you sub in the numbers for m, whatever you sub in for m, you get a discriminant value. All right, so I'm trying to, instead of subbing in each one individually, like if you subbed in, if m was 1, you would have said discriminant equals 4 times 1 squared minus 36. You can already see 4 take away 36 is going to be less than 0. So clearly, no solutions, right? But what you don't want to do is you don't want to do this. You don't do 1 and 4 take away 36 is negative 32. You don't want to do plot a point. You've just done 1 point. And then we do it again. We say, oh, let's try another number. You don't want to be trialing 10 different numbers to picture a graph. That's what you did back in year 7. When year 7 you had a table of values and you kept plotting every single point and then use a ruler. That takes too long. That's why we're testing you to understand the graph and you can sketch it in one go. So to sketch this graph, this is clearly a quadratic graph. It's m squared. So if it's quadratic, there's only 3 key things you have to find. Y-intercept, turning point, x-intercepts. In this case, it's going to be called discriminant intercept, m-intercept, and the turning point for this graph. So, bringing back your knowledge from what you've learnt so far, what is the discriminant intercept, or the y-axis intercept? What's the y-axis intercept? Negative 36, because you know that m needs to be 0, and if m is 0, you can see that it'll end up being discriminant equals to 0, negative 36. So already we can say turning point, or not turning point, so the y-intercept is negative 36, so 0, negative 36. What about x-intercepts? So we know it's a smiley face because the number in front of the squared is positive, so smiley face. What are the m-intercepts? Yes, Raha? Okay, so let's see how we get there. So to find the intercepts, so when does the graph touch it? It's when the discriminant is 0. See that? This is the axis. It's when y equals 0. So in this case, it's the discriminant equals 0. So if you sub in discriminant to be 0, you get 4m squared minus 36. Add 36 on both sides. Divide both sides by 4. And square root both sides. But when you square root the 9, remember you have a plus minus answer. So plus minus 3. So if we were to sketch this so far, I've got the y-intercept. I've got x-intercept as negative 3 and 3, right? And to find the turning point, well, hopefully you realize this is already in a turning point form. Doesn't move left or right. It moves down by 36. See that? That's your down. And when you're squaring, it doesn't move left or right. That's one of your exercises, 7b. Yeah, so if you go back to 7b, this is a turning point form already. So your turning point must actually be at 0, negative 36 as well. So if we sketched it, this is what the graph looks like. Now, this is not the graph of your quadratic equation. This is the graph of your discriminant equation. Meaning, instead of testing 10 values before, we've just tested infinite values. This graph gives you all the infinite values that you can see. Does that make sense? Because what you did before was we only did 1, then we did 2, and we did negative 5. We chose negative 5, and it was up here, and then when I asked you for 10, 10 was over here, right? So each value that you're choosing like individual points, but isn't it easier to have a graph to visualize? Because if we look at the graph now, if I said, if m equals to 1, here's 1. But where does that lie on the graph? It's right here. But if it's there, when m is 1, what's the discriminant? I don't care about the value. All I care about is it negative, or is it positive, or is it 0? What is that? It's negative. So if it's negative, if discriminant is negative, what does that tell you?
No solution.
No solutions. So that's why when I asked you before and I said, when m is 5 or negative 5, you see, how do you know with this graph? Where's negative 5? Negative 5 is over here. So if negative 5 is over here, where is it on the graph? See, on the graph, I don't need to know what the value is. I'm just looking at the graph and saying, well, the discriminant will be positive. So I expect 2 solutions. So that means I can ask you very many different questions now. I can say, when will I have 1 solution? Clearly, negative 3 and 3, which we saw before. It was at negative 3 and 3. And then if I want any number in between, then I know it's going to be no solutions. Between negative 3 and 3, you're not going to get any x-intercepts. And any number greater than 3, you will definitely get 2 x-intercepts. And that right there is very hard for the mainstreamers at Year 11 methods at week 6 to understand, because they're seeing this graph and they're thinking what you guys did so far. But they have to separate that thinking. One is the graph and one's the discriminant. The discriminant affects what your graphs are. Instead of doing it individually, you did it infinite. You have infinite graphs in front of you right now. So that's why you can just predict what the graph should end up being. Does that make some logical sense? It is hard to take, but if you can take it in, that's really good. Otherwise, as you build your skills to sketch, you'll be able to analyze this function. So far, so good? All right, so to answer the questions, we can already say, just based on the graph, which I'll draw again neatly so you can see. So we found out for our m-axis, discriminant axis, we found 3, negative 3, and we know this is 0, negative 36. And remember, this is m, this is your discriminant. So answering the questions, you got 3 sections, I, double I, and triple I. First one says, when will you have 1 x-intercept? Clearly, right here. Not in between. It's when m is 3, discriminant is 0. Yeah, remember, because we need discriminant to be 0 for 1 solution. And that's the coordinate for 3, 0. This is the coordinate for negative 3, 0. So this is when m is negative 3, discriminant is 1 solution. Right, so we're just looking at the coordinates. Yeah, so for the first one, you'd say when m equals negative 3 or 3, you get 1 x-intercept. What about when they say for no solutions? To get no solutions, it's this region. Any number you choose in between will correspond to a y value or discriminant value that's negative. And if discriminant is negative, you get no x-intercepts. So the answer for this case would be when m is bigger than negative 3, but less than 3. Can't equal to it, because if it equals to it, you get 1 x-intercept. So you can even try on Desmos. If I tried on Desmos and I did negative 3, it's positive, negative 2.99. That's in between. It looks like it's 1. But if you really zoom in, it's going to be none. Because I said, pick a number between negative 3 and 3, and negative 2.99 is just shy of negative 3. And so that's why I know it's going to have no intercepts. Does that make sense? Yeah? Okay, so, and the last one. 2 distinct solutions. Means you want 2 answers or 2 intercepts. This is where students struggle with writing the actual region, but anyone have an idea? Beautiful. So if you were to write it, you have to write it separately. A lot of students try to do it this way. I think they do it, say it again, it was less than negative 3, so they do, how do they do it? I think they do it like this, less than negative 3, and then greater than 3. That's inappropriate. You can't do it that way, okay? Conventionally, smaller number is on the left, Okay, and if you write it that way, that's the wrong way of writing it. If it's two regions, so you can see any number that's greater than 3, then you have to write that as m greater than 3, or the other region, which is over here, then you have to write m less than -3. You have to write it separately. You can't write them together. Okay, so you can only write them together when it's on a continuous interval. If they're separated intervals, then you write them separately. Okay? How's that feel? That was a lot of theory. Yes? So that's the skill. And what makes it easy? Once you sketch it, the answer to the 3 is easy, rather than trial and error. So what we did before was trial and error. We're only picking 1 or 2 points. We're not doing that now. If you do the graph, you get the infinite points. If you get infinite points, you can predict. Okay? All right, flip over as your last example, and then I'll leave you to try it out. I'll make a worksheet where it plays around with these type of questions so you can practice. But let's have a look at this second example, and that's my last one for today. Let's do it again. Here's your equation. You got y equals 3x squared plus m minus 3x minus m. Okay, so this is crazy now. We've got so many m's there. And if you had to trial and error, that would take ages to do. The fact that you have to pick many points. So the goal first, create a discriminant function. Let's analyze the discriminant. So here we go. How do you find the discriminant again? B squared minus 4ac. What is my A? What is my B? What's my C? Be careful the B. Okay. What's my A in this case? Can I please have, yes, Andrea? 3. Very good. So it's the number in front of x squared. B. Who wants to have a go with this one? Sign me.
Is it m minus 3x?
Ooh, not the x. It's always what's multiplying to the x. Yeah, so
So just m minus 3?
beautiful. Just m minus 3. So this is the number, that's the coefficient in front of x. No matter how crazy it is in front of x, that is your value. Okay, that's the B value. Then C should be easier. What is C in this case, Ahad? Beautiful. So a lot of students forget that negative. A lot of them just say m. It's actually negative m. So that's your C value there. Okay, let's put it into the discriminant function. Let's see what we get. So B is m minus 3. You're squaring it. Minus 4 times A, which is 3, times C, which is negative m. Let's expand the brackets. Remember back in, was it exercise 5a, I think it was? So expanding this bracket quickly, m minus 3 squared gives you, who wants to have a go? Yes, Yuna?
N squared minus 6x plus 9.
Beautiful. That's what I want to see. Okay, so at year 11, that's prerequisite that you should just know that by looking at it. Next one. Oh,
6m.
oh, sorry. I'm so used to writing x. Thank you. 6m. And then negative 4 times 3 is negative 12. Negative 12 times negative m is positive 12m. Double negatives become positive. Yes, so negative 4 times 3 is negative 12. And negative 12 times negative m is positive 12m. But we can combine these two, collect like terms, negative 6m and 12m. That gives you now an equation where you have m squared plus 6m plus 9. This is your discriminant function. What you don't want to do is you don't want to sub in numbers and trial and error. That'll take too long. The quicker way is to sketch this graph. Okay, so I want you now, I'm going to give you about 2 minutes. Sketch this graph. You need 3 things. X-intercept, Y-intercept, turning point. Okay? X-intercept, Y-intercept, turning point. I'm going to pause the video. Let's see if you got these answers here. So, this is my graph. Can I get a show of hands? Who got this graph? It did not go down. It should just have gone left by 3. Got the turning point. That's your intercept as well. Well done. That looks good. So I don't need to go through most of that. If you want to look at it, it's on OneNote. So I found the y-intercept. Turning point I did complete in the square. And pretty much from here you should be able to sketch. But I found the m-intercept as well. Now, let's answer the question. You got the graph. So now you don't have to trial infinite points. You can actually just look at the graph and then figure out how many solutions you can potentially get. So let's answer this question here. They're asking how many rational values. Rational values just means fractional numbers. Fractional numbers or whole numbers. Now, let's think about m. If you want to show this equation has always a rational answer, what that means is they're saying your x-intercept, you'll always have an x-intercept regardless. Does that make sense in this situation? Why is it that no matter what m value you choose, you're always going to get an intercept? How's that possible?
Because it's the square of it.
Yeah. You see this here, even if you just looked at this equation, which is interesting when I give it to my year 11s, have you noticed the discriminant? Whatever m is, m plus 3, no matter what number you come up with, whether it's negative or something like that, or even decimals, you're going to square that answer. And every time you square it, it's going to be positive. But if you have a positive answer, you're going to get 2 x-intercepts already. The worst case scenario you can get is m equals negative 3. Negative 3 plus 3 gives you 0, and 0 squared is still 0. But then if discriminant 0, how many solutions do you get? 1. So the worst case scenario is you get 1 intercept, and every other scenario you're always going to get 2 intercepts. But that's the explanation you have to do at year 11, because you need to tell us you know that. You need to be able to look at an equation and think, how does a discriminant affect the overall graph? Or if you had a graph ready, then you can already see the graph never even ventures into negative discriminant. There is no values of m that you can choose that the graph ends up in this region. So you're never going to get negative discriminant. If you never get negative discriminant, it means you never get a no solutions. So that means you're always going to get a solution. So either you talk about the equation, you say it's a perfect square, which means this, so it's a turning point form that sits on the x-axis. That's what a perfect square will look like. You either describe it like that, or you describe the fact that for all m values, discriminant is always 0 or more. And that will show you understand. Okay, so that's at the year level. You can see the difference between 9 and 10. That was just learning skills. And then year 11, we're doing a bit more analysis. We're doing more thinking deeper. That's what you have to learn. And that's hard for the students who struggle with algebra. Okay, so algebra is very hypothetical. This is the efficient way of solving the problem. Cool? I'm going to leave it there. So there's more problems in that exercise for you to try. And the exercise that you'll have a look at, which one is it? This question here. Question 5 is where it begins. Everything before is like year 10 revision. And then all of this is really testing your understanding. Okay, so maybe start at 5 if you're just having a go with what I just taught you. But we'll have the second half of Monday after I go through your second applications test. You have a bit more time to play around with it. And then we finish off with 3J next week, Friday. Yeah. All right, I'm going to stop the video. Thanks.